Speaker is, sorry. Today's speaker is Sam Partee. He's a machine learning engineer at Hewlett Packard Enterprise. Sam's team was part of the Cray AI Innovation Lab before being acquired by HPE. Sam holds a degree in computer science with a focus on high performance computing and machine learning. So with that, I'll hand it over to you, Sam.
Thank you, John. So I mentioned this earlier, but I just want to mention again, there is a link in the chat if you have any questions at any time before, during, or after the talk. You can hop in there and my team will be there to answer any questions that you may have. But today, as John mentioned, my name is Sam Partee, and I'm here to talk a little bit about SmartSim and how it can be used for online analytics and machine learning inside and around HPC simulations. So let's get started. So what is SmartSim? It is an open source library dedicated to accelerating the convergence of AI analytics and data science with HPC simulation models. So that's a little buzzwordy. What does that mean? It means we can connect models written in Fortran, C, and C++ to what we like to call the modern data science stack in an online fashion. So meaning not using the file system. We can essentially embed calls to machine learning models inside Fortran, C, and C++ simulations, run those models from inside Jupyter notebooks, easily communicate data along with metadata between C, C++, Fortran, and NumPy, and do all of this without ever touching the file system. The diagram below shows a little bit of how you do this in an online analysis setting, but if it's not making sense right now, don't worry, we'll get into it. So I'd like you to imagine this box is a supercomputer with a workload manager or scheduler like Slurm or PBS, and it could also be like a cluster. And in this case, we're going to be launching some things onto the supercomputer. First, SmartSim is capable of launching what we call the Orchestrator, which is built on top of Redis. It's an in-memory database written in C. It's a key value store. So essentially it's a large hash map. And then the way I like to explain it to people that aren't familiar with Redis, it's like a gigantic Python dictionary that can be distributed out onto a supercomputer, as you can see. And its module system allows SmartSim to deploy ML runtimes like PyTorch, TensorFlow, and ONNX inside the database. When you bring a simulation into this through SmartSim launches these with addresses for the database cluster and all shards, such that any instantiated client is immediately connected on any rank of the simulation. In this case, through the use of SmartSim clients in C, C++, Fortran, and Python, users can embed clients and simulations to communicate the data to the in-memory database, as well as store, execute ML models and scripts on CPU or GPU using the ML runtimes package within the database. Vis-a-vis, this provides you distributed storage and machine learning inference and processing in a distributed performant way. In addition, the Smart Redis clients provide a dataset object, but not too dissimilar from the X-ray dataset object. And really what this does is helps users group together n-dimensional tensors with associated metadata, which is useful in scientific simulations. And the data movement strategies among the shards of the in-memory database are opaque to the user. So you never have to know exactly which shard your data is stored on or where those shards are even located. SmartSim will launch and connect all of those entities for you. Once again, none of this is going over the file system. So you're not saving anything to file, and you're not having to incur the cost of using that slow share file system. So it's important to note that SmartSim is composed of two libraries. We use the term SmartSim as an umbrella term to talk about this client-server paradigm, but really there are two libraries. The first is the infrastructure library, which is typically called SmartSim, which provides the ability to launch machine and deep learning infrastructure out onto supercomputer and cluster systems. It works directly with launchers, as you see on the bottom there, such that we can launch this through a Python interface, making it really easy to just spin these types of workflows up. In addition, it provides those storage mechanisms I mentioned, in addition to KeyDB, which is a multi-threaded version of Redis, and then that machine learning infrastructure. Everything you see in the light blue gridded sections are ones that we're working on right now, including Ray, which I'll touch on in a little bit. So the client library, SmartRedis, is what actually communicates. It's the client of the client server paradigm. And we have these clients in Fortran, C, C++, and Python, and they provide a tensor and dataset API, which I will show later. The tensor API, it's important to know, is just the natural array format of that language. So if you're sending data through the database and you send it from Fortran, you can easily pull it out in NumPy. And if you send a NumPy array to the database, you can easily pull it out in Fortran. Likewise, you could do the same thing in a nested or contiguous array in C or C++. This allows you to seamlessly exchange data between these languages at runtime. They are built on top of Redis clients that assume the Redis AI API. So what does the infrastructure library actually do? Well, the infrastructure library its job is to launch machine and deep learning infrastructure alongside HPC simulations. So its kind of secondary job is actually to launch your application in a way such that it will find the database automatically. But the primary job of the SmartSim, the infrastructure library, is actually to utilize CPU or GPU compute nodes out on the system to launch the Orchestrator, which is that in-memory database that I talked about, and connect it to that application deployed by SmartSim. In this way, you can seamlessly add ML and DL functionality by only including a very lightweight client library into your workload. It's a single static shared library. This orchestrator can run on CPU or GPU, and as I mentioned, is packaged with those ML runtimes such that you can use any PyTorch, TensorFlow, or ONNX, which you can think of like scikit-learn or Spark, or really anything that's, you could even use PyTorch in the ONNX runtime, anything that is able to be in the ONNX format. And you can actually execute those models within this orchestrator, this in-memory database, on CPU or GPU. So what does SmartRedis do? Well, SmartRedis is the actual connection between, it's the client paradigm that you include inside of your simulation or workload, and it connects your simulation to this orchestrator. It includes the commands, you'll actually see the API later, but it includes the ability to also connect as many clients as you may like. In this way, you can also have an analysis environment that's running in parallel to this, say ML-enabled simulation, and constantly monitoring both the model. There's statistics for latency as well, and active monitoring, as well as sentinels for failover and replication. In this way, you can also make sure that your simulation is doing what you intend by actively pulling fields out of your simulation and monitoring them from within a Jupyter notebook. So this is the data set, or I should say the SmartRedis API, and there's two different sets here. The first is the client data structures along with associated methods, and then the data set, which is that user space object that we provide. It's important to note again, tensors are just the natural array format of the given language. So tensor, you can see it's put get semantics. It's an n-dimensional tensor. You can put and get. There's also an unpack for the compiled languages, which actually unpacks a tensor into memory that the user already owns. Model, so any of those aforementioned frameworks, you can put and get and run a model in any of those languages. And then scripts, an arbitrary number of Python functions and TorchScript can be included inside a script. And you can individually call any of those functions within a script on any data stored within that database, such that you can do online processing with a very performant JIT-traced Python. So the data set that you see here is a user space object that I mentioned helps group n-dimensional tensors along with associated metadata. That should sound pretty familiar, and I'll touch on why this is actually going to work possibly well with X-ray in the future. But for now, I'm going to gloss over the data set just a little bit. The supported data types are there on the left, and it's important to note that this API is the exact same in Fortran, C, and C++, along with Python. The only difference is the number of parameters, because Python can infer types and things like that. Okay, what can I do with SmartSim? That's an all too important question. Well, the first thing is online analysis. I already mentioned that. But in this way, I have a simple lamps bounding box simulation that you see here, but really it could be any MPI plus X simulation. It honestly really doesn't even have to use MPI. And you can include the clients. Usually what we do and what we've seen users do is we include one client on every rank of the simulation. In this way, you can have every rank sending the data local to that rank without having to do expensive MPI collectives and whatnot to the database, and then reconstruct that in a language where it's much easier to reconstruct your domain, like in Python. In addition, all of those aforementioned processing abilities are available in the database, so that if you need to do some online processing before you do your visualization or analysis of the data being streamed from the simulation, you can do so. It's important to note that, once again, none of this goes over the file system, and you don't incur that cost. So online processing, I gave a simple example over to the right. I won't go into that example too much because I don't think I have the time in a 50-minute talk. But what you can see is actually the red, like the little red outlined code. That's part of the infrastructure library that actually spins up that machine learning infrastructure. And then the blue code is the client code, which actually utilizes that machine learning infrastructure. It's important to know that that blue code is available in C, C++, Python, and Fortran. So that could be a whole nother program doing it, distributed out onto a supercomputer without any, knowledge of you having run the red code. The only reason we ran it serial is so that you could see the whole thing in a little, piece of code. So online processing, here we're giving the example of streaming singular value decomposition, is used to get a lower rank approximation to a given tensor. And in this case, we use the TorchScript SVD, and we can use any function available that you can mutate a tensor with in TorchScript, which is a lot of functions. So you can do a lot of different processing. And in this way, you can do the same streaming type processing that you would for streaming analytics. But in this way, you can call those scripts stored within the database to act on that data being streamed from your simulation or workload. Oh, last thing, this can run on CPU or GPU. So if you wanted to run the SVD on GPU, it's very easy. You just specify GPU in the Orchestrator commit line. So online training is another use case we see a lot. In this way, you stream the data from your simulation into the database, and then you train. A lot of the times it's on data local to each rank, and you can train using distributed frameworks like Horvath and the DL plugin for Cray. And when launched with SmartSim, it immediately connects that training service or that training job to the database, such that any client instantiated inside that application launched through SmartSim will be immediately connected to this distributed Redis cluster. You can checkpoint and store models within the database and then immediately use them within some workflow. So you can actually train these models and then take a resultant model, after some number of epochs or a checkpoint or what have you, early stopping, and then send that model, a JIT traced form of it usually, where it's going to live in that database in a C-based runtime. And then you can call it from whatever workload. It could be a third application. It could be the original data streaming application, what have you. And in this way, you can do a full online training loop. And once again, the model can be written in Python and set from Python, but then called from Fortran or C or C++ or vice versa. There's really no difference between the clients in that way. Last thing to mention is we're also looking for feedback on the design of the data loaders. So if you have a second, you should check those out. Online inference. So once again, a small example code. This is one of the first things that we tackled. Same paradigm over there with the red and the blue code. In this case, we send a simple PyTorch, a really simple component. And this is just models in PyTorch, TensorFlow, and ONNX, scikit-learn, Spark, and others. They can be written in Python, called from Fortran or any of the client languages. And as I mentioned, they execute in that C-based runtime. The calls to the database from whatever application are distributed evenly among all shards of the database cluster. And they could possibly be utilizing GPU nodes for that computation. And they are distributed evenly, those requests, because of direct addressing by the clients. So there's no proxy application, or there's no load balancer between the actual application and the database. It's all direct addressing, so that you can be assured you're not incurring the cost of a move or ask or a redirect. The code example shows a serial example of how to use SmartSim to spin up that database locally, either on a laptop or a single node, and then store, execute, and retrieve the result of a simple PyTorch component. So now I'm going to talk for a little bit about our latest research. So our latest research we did with the National Center of Atmospheric Research, of which many of you are familiar. I included the links. I won't go over all of them just because this talk will be recorded so that you can go back and click all of them, but it is on archive. So please feel free to check it out and give us some feedback. We started with this setup that you see here. So this is the first setup that we used in our attempt to replace the Miki parameterization that is I think started in Jensen et al. In 2015. And the simulation that we were targeting was modulars model 6 in that for 1/4 degree that Alistair did. And the training simulation that we used to train the model, in this case that we called EQ ResNet, a modified ResNet, was trained on 1/10 degree data. So a really high resolution data. And the goal was then to use that 1/10 degree trained EQ ResNet model to predict the value of eddy kinetic energy within a 1/4 degree simulation. So talking a little bit about the computational setup here, you have MOM6 on 3,551 ranks, each with one Fortran client from SmartRedis. Over the course of the simulation on the baroclinic timestep, which I believe is every 2 hours of the simulation, it sends features of mean kinetic energy at the surface, deformation radius, slope, and relative vorticity to the database, in which case the database is sharded on 16 nodes, each with one GPU. So in this case, you have the database over 16 nodes, and I think MOM6 was on 70 in this case, but a total of 3,551 ranks for MOM6. So in this case, every time step, MOM6 is using those Fortran clients to send those features to the database, where they're then pre-processed by TorchScript and fed to this EQ ResNet model, which predicts the value, given those features local to a given rank, of eddy kinetic energy at that rank. And then MOM6 retrieves those values of eddy kinetic energy and consumes them for use inside the next time step. This shows you a little bit of the results. It's 1 year of the simulation that we did. And you can see this is the 1/4 degree simulation. So it is eddy permitting. And usually within an eddy permitting model, you're not seeing, if you just ran it with the Miki parameterization, you wouldn't necessarily see some of the features at the equator or the features at the high latitudes that you see here. And so this is one of the results from that streaming online inference that we did with the Miki replacement. So then for the paper, we decided to step it up a little bit and actually include one of SmartSim's features, ensembling, which allows you to create and configure ensembles of simulations relatively simply. And so in this case, we kind of upped the ante by, instead of just running one MOM6 model, we ran 12. And we reduced the ranks. So we took the grid down a little bit, down to 910 ranks. But in this case, it's 12 910 rank models, each with one Fortran client from SmartRedis on each rank of the simulation, talking to the same 16 database node cluster with the same EQ ResNet model. And in this case, you can see over 10 hours of simulation time, which is about 7 hours of compute time here. We did about 970 billion inferences throughout 10 simulated years, and for the full 100 years, it's a little under 10 trillion inferences. This is for every grid point in the domain of the simulation, which is the 1/4 degree simulation, and every grid point in each of the 12 ensemble members is being predicted for the value of eddy kinetic energy at every 2-hour time step within the model. And then, so here's some of the results. So this is kind of the main result figures of the paper. So first, the 3 globe figures. On the top left hand, you have the, quote unquote, truth data, which is the eddy resolving simulation at 1/10th the degree. We consider this to be the truth data because it is eddy resolving in this case. And then on the bottom there, you have the 1/4th of the degree with the Meeke parameterization, and the article there is listed. And then on the top right-hand corner, you have the ensemble average from all 12 ensemble members that are augmented with this streaming ML-EKI approach, or SmartSim EKI approach. And you can see that clearly we are getting a lot closer to just even visually the 1/10th degree eddy resolving simulation. If you didn't like it visually, you can also see that on the graph down there on the bottom, which is zonally averaged on a log 10 scale. The blue line is the SmartSim EKI of eddy kinetic energy on a log 10 scale, zonally averaged. And the ER is the eddy resolving simulation. And so you can see how Meeke kind of falls out right around 0 there, and how we are approaching the eddy resolving simulation values a lot closer. Yeah. So some of our current research and development. This functionality is currently in progress, so please let us know if you want to try it. Here, we're actually now going to be able to launch reinforcement learning algorithms with Ray. So just like we launched the Orchestrator, SmartSim can also launch Ray, which just launches Ray workers on every node and every CPU, and then allows you an interface to then send jobs to it programmatically. I won't go into this too much, but please let us know if you have questions. And then lastly, one thing that we were really interested in, we wanted to bring up here was that we also are interested in creating an X-ray interface to our clients, such that you can do things like get X-ray from an existing data set. We have some of the ideas fleshed out here, but essentially what this would do is take our data set object and allow it to be converted into an X-ray. So essentially, this would allow you to take data from your simulation with associated metadata, like say a grid or coordinates, and send that through the database, in a streaming fashion, such that a Jupyter lab could be iteratively pulling that data out into X-rays for plotting. And we think this would be really, incredibly useful for online analytics of these simulations. Lastly, some more resources. If you want to hear more, we've given a few talks, and if there's a few posters out there, and there's a tutorial. So please let us know if you have any questions, and thanks for the time.